You trust empty space. You trust that the void between atoms is harmless, that the vacuum of the cosmos is just passive nothingness waiting to be filled. You breathe and assume the air between molecules is dead silence. You look at the night sky and see emptiness as the absence of danger. But you are wrong. The emptiness is alive. It is seething with energy, bristling with invisible particles that appear and vanish billions of times every second. And the terrifying part is not that this happens. The terrifying part is what it means. Because physicists have discovered that under the right conditions, empty space can be ripped open. It can be forced to bleed matter into existence. It can be heated by motion alone. It can remember being watched. And worst of all, it can collapse, rewriting the laws of physics across the entire universe at the speed of light, without warning, without mercy, without any possibility of escape. The vacuum is not the floor beneath reality. It is a trapdoor, and the latch is already loose. You need to forget everything you were taught about empty space, not because it was wrong in a casual, hand-waving kind of way, but because it was wrong in the way that matters most. It was wrong in the way that hides something dangerous. When you were a child, someone probably told you that atoms are mostly empty space. They said the nucleus is a tiny dot in the center, and the electrons orbit far away, and in between, there is nothing. They probably used an analogy like a marble in a football stadium. The marble is the nucleus, the stadium is the atom, and the rest is void. And you believed them. Why wouldn't you? It matched your intuition. When you look at the night sky, you see blackness between stars. When you look at a room, you see air between objects. The default state of the universe appears to be emptiness. Nothingness seems to be the canvas, and matter is just the paint splattered onto it. But that picture is a lie. It is one of the most persistent and dangerous lies in all of science education. Because what we call empty space, the vacuum, the void between particles, is not empty. It never was. And the deeper physicists dig into the mathematics of quantum field theory, the more they realize that this so-called nothingness is the most complex, energetic, and terrifyingly unstable thing in the entire universe. To understand why, we have to abandon the old language. We have to stop thinking about particles as tiny balls and start thinking about fields. This is the single most important conceptual shift in modern physics, and most people have never made it. In quantum field theory, which is the mathematical framework underlying the standard model of particle physics, particles are not fundamental. Fields are fundamental. An electron is not a little sphere. It is a localized vibration in the electron field, a field that permeates every cubic centimeter of the cosmos. A photon is not a pellet of light. It is an excitation in the electromagnetic field. Every type of particle you have ever heard of, quarks, neutrinos, muons, the Higgs boson, each one is simply a ripple in its corresponding quantum field. These fields are everywhere. They overlap, they interact, and they never ever turn off. Now here is the key. Even in their lowest energy state, even when there are no particles, no ripples, no excitations, these fields are not silent. They hum, they fluctuate, they jitter. This is not a metaphor. It is a direct mathematical consequence of the Heisenberg uncertainty principle applied to fields. You cannot have a quantum field that is perfectly still, because perfect stillness would mean you know both the field's value and its rate of change with absolute precision. Quantum mechanics forbids that. So the fields must fluctuate. They vibrate around zero energy in a restless, chaotic shimmer. And in that shimmer, particle-antiparticle pairs are constantly being born. An electron and a positron materialize, from the jitter, exist for an unimaginably brief instant, and then crash back into each other, annihilating and returning their borrowed energy to the vacuum. A quark and an antiquark flicker into being and vanish. Photons appear and disappear. This happens everywhere, at all times, in every point of space. It is happening right now, between the atoms in your hand. It is happening inside your skull. It is happening in the void between galaxies. These are called virtual particles. The word virtual makes them sound harmless, like a simulation, like something that almost exists but does not quite make it. But that word is misleading. Virtual particles are not fictional. They have measurable effects. They shift the energy levels of hydrogen atoms. They alter the magnetic properties of electrons. They exert physical forces between metal plates. The Casimir effect, first predicted by Hendrik Casimir in 1948 and confirmed experimentally in 1997, demonstrates that two uncharged metallic plates placed extremely close together in a vacuum will be pushed toward each other by the pressure of these virtual fluctuations. The vacuum literally pushes objects around. It has weight. It has force. It is not nothing. It is a seething, pressurized ocean of almost existence. And now we arrive at the Schwinger Effect. Because the obvious next question is this: if the vacuum is full of these virtual pairs constantly flickering in and out of existence, what would happen if you grabbed a pair before it could annihilate? What would happen if you ripped the two halves apart and forced them to become real? The answer was calculated by Julian Schwinger, one of the founding architects of quantum electrodynamics, in 1951. Schwinger showed that if you apply a sufficiently powerful electric field to the vacuum, the field can do work on the virtual electron-positron pairs. Normally, these pairs are born together, drift apart by an infinitesimal distance, and then snap back together like a rubber band. Their existence is borrowed on credit from the uncertainty principle, and the debt is repaid almost instantly. But in the presence of an overwhelming electric field, the electron gets pulled one way, and the positron gets pulled the other way. If the field is strong enough, it pulls them far enough apart that they can no longer recombine. The rubber band snaps. The virtual pair becomes a real pair. Two actual particles with real mass, real charge, and real momentum materialize out of the vacuum. Energy has been extracted from the electric field and converted into matter. The void has been ripped open. Think about what that means. You did not collide anything. You did not smash protons together in a particle accelerator. You did not inject energy into a material substance. You simply applied a strong enough electric field to empty space, and empty space bled. Matter appeared where there was none. Existence was pulled out of non-existence by brute electromagnetic force. The vacuum is not a blank canvas. It is a dam, and the Schwinger effect is the calculation of how much pressure it takes to crack that dam. The critical field strength is staggering. Schwinger calculated that you would need an electric field of approximately 1.3 times 10 to the 18th volts per meter. To put that in perspective, the strongest electric fields we can currently generate in a laboratory are roughly 10 to the 15 volts per meter, using the most powerful laser systems ever built. That is still about 1,000 times too weak. This is why you do not see electrons popping out of thin air during a thunderstorm, or when you shuffle your feet across a carpet. The threshold is astronomical. The vacuum is resilient. It does not surrender its contents easily. But here is the part that should worry you. The fact that the threshold exists at all is the terrifying thing. The vacuum is not infinitely stable. It has a breaking point. It has a limit. And we know exactly what that limit is. The equation Schwinger derived gives an exponential suppression factor. The probability of pair creation per unit volume per unit time goes as the exponential of negative pi times the critical field divided by the applied field. When the applied field is far below the critical value, that exponential factor is vanishingly small. So small that you could wait for the entire age of the universe and never see a single pair produced. But as the applied field approaches the critical value, that suppression weakens, the probability climbs, and at the critical threshold, the vacuum begins to discharge like a battery. This is not speculation. This is one of the most precisely formulated predictions in the history of theoretical physics. It emerges directly from the mathematics of quantum electrodynamics. The same theory that predicted the anomalous magnetic moment of the electron to an accuracy of better than 1 part in a trillion. QED is the most precisely tested theory in all of science. When it tells you the vacuum can break, you should listen. And scientists are listening. There is an active global effort to reach the Schwinger limit. The Extreme Light Infrastructure, known as ELI, is a network of laser facilities spread across Europe. The facility in Romania houses one of the most powerful lasers on Earth, capable of producing pulses with a peak power of 10 petawatts. That is 10 million billion watts concentrated into a beam thinner than a human hair for a duration shorter than a trillionth of a second. Facilities like the Station of Extreme Light at the Shanghai Super Intense ultra-fast laser facility in China are pushing even further. The explicit goal of these projects is to reach electric field intensities where the vacuum begins to respond, where virtual pairs are promoted to real pairs, where emptiness starts to glow with freshly created matter. We are not there yet, but the gap is closing. Each generation of lasers brings us closer by orders of magnitude. And here is the deeply uncomfortable truth that physicists discuss in technical papers but rarely emphasize in public. The Schwinger Effect does not require a laboratory. Any electric field of sufficient strength, anywhere in the universe, at any time in cosmic history, could trigger this process. Near the surface of a magnetar, a neutron star with a magnetic field exceeding 10 to the 15 Gauss, the electromagnetic field strengths approach and possibly exceed the Schwinger limit. In those environments, the vacuum is not stable. It is actively producing electron-positron pairs. The space around a magnetar is not empty. It is a factory. Matter is being manufactured from nothing by the sheer intensity of the fields. Now, pause and consider the implication. We usually think of matter as something ancient, something that was forged in the Big Bang, cooked in stars, and assembled into planets and people over billions of years. We treat it as inventory. It was made once, and now we are just rearranging it. But the Schwinger Effect tells a different story. It tells us that matter is not inventory. It is a phase transition. It is what happens when the vacuum is stressed past a certain point. Matter is not a permanent resident of the universe. It is an emergency response. It is what the vacuum does when it is pushed too hard. The boundary between something and nothing is not a wall. It is a threshold, and the vacuum is on the wrong side of it. There is another layer to this that makes it even more unsettling. The Schwinger Effect is not limited to electromagnetic fields. The same mathematical framework applies to any sufficiently strong field. Gravitational fields, chromodynamic fields. The principle is universal. Wherever a quantum field exists, and they exist everywhere, the vacuum can be stressed to the point of particle creation. This means that the instability is not a quirk of electromagnetism. It is a fundamental property of the vacuum itself. The vacuum is a pressurized vessel, and every force in the universe is a potential crack. Let us also talk about what happens after the pairs are created. When the vacuum discharges and real particles appear, those particles carry energy. That energy comes from the field that created them. In the electromagnetic case, the electric field loses energy as it produces electron-positron pairs. This is called vacuum discharge or Schwinger pair production, and it acts like a form of electrical breakdown. Think of it as the quantum mechanical version of a spark jumping between two electrodes. In a classical spark, the air between the electrodes ionizes and becomes conductive. In the Schwinger effect, the vacuum itself ionizes. Space becomes conductive. The field shorts out through the fabric of reality. This has staggering implications for astrophysics. If the electric field near a magnetar exceeds the Schwinger limit, the vacuum begins to conduct. Pairs are created. Those pairs are accelerated by the field, radiating photons, which in turn create more pairs in a cascading process. This is called a QED cascade, or an electromagnetic avalanche. It is a runaway chain reaction in which the vacuum is consumed as fuel. The energy of the field is converted into a blizzard of particles and radiation. The vacuum does not just break, it shatters. And the shrapnel is made of matter and light. These cascades are believed to occur during magnetar flares, the most violent electromagnetic events in the known universe. In December of 2004, a magnetar designated SGR 1806-20 flared so brightly that it disturbed Earth's ionosphere from 50,000 light-years away. 50,000 light-years, that is halfway across the galaxy. And the energy released in that burst, in less than a second, exceeded the total energy output of our sun over 250,000 years. Some models suggest that the vacuum itself participated in that event, not as a passive backdrop, but as an active ingredient. The vacuum was ripped open, and the escaping particles amplified the explosion. This reframes the universe in a way that should make you deeply uncomfortable. We are accustomed to thinking of space as the safe part. Space is where things are not. It is the gap between dangers. You worry about asteroids, about solar flares, about supernovae. Those are objects. Those are things. You do not worry about the emptiness between them. But the Schwinger Effect tells you that the emptiness is not safe. The emptiness is the most energetic part of the picture. It is just holding itself together for now. Because the fields in your neighborhood happen to be weak enough. You live in a calm patch of a pressurized ocean. The pressure is everywhere. It is under your feet, inside your lungs, between the synapses in your brain. And if the pressure ever spikes, even locally, even briefly, the vacuum will respond. It will crack, and what comes pouring out will not be nothing. Now, there is a subtlety here that is important. The Schwinger effect, as originally derived, applies to constant uniform electric fields. Real laboratory conditions are not like that. Real lasers produce oscillating, focused, short-duration pulses. In these time-varying fields, the pair production mechanism changes. It blends with another phenomenon called multi-photon pair production, where multiple photons combine their energy to create a real pair. The physics becomes more complex, but the principle remains. The vacuum has a breaking point, and we are engineering our way toward it. There is also the fascinating connection to the Dirac sea, the historical precursor to modern quantum field theory. Paul Dirac, in 1928, proposed the vacuum is not empty, but is instead a sea of negative energy electrons filling every available quantum state. A positron in Dirac's picture is a hole in this sea, a missing negative energy electron that behaves as if it has positive charge. The Schwinger effect, in this older language, corresponds to the electric field lifting an electron out of the Dirac sea, leaving behind a hole. The pair is created because the field has enough energy to promote a particle from the hidden sea of negative energy states into the visible world of positive energy states. Modern quantum field theory has replaced the Dirac sea with the more sophisticated language of field excitations, but the intuition is the same. The vacuum is full, it is saturated, and under enough stress, it overflows. We should be precise about something. As of now, no experiment has directly observed the Schwinger effect in its pure, non-perturbative form. The field strengths required are simply beyond our current reach, though only barely. What we have observed are related processes. Pair production from photon-photon collisions, pair creation in heavy ion collisions at facilities like the relativistic heavy ion collider, and multi-photon pair creation at laser facilities like SLA, the Stanford Linear Accelerator Center, where experiment E-144 in 1997 demonstrated pair creation from the collision of high-energy electrons with a terawatt laser pulse. These are all cousins of the Schwinger mechanism. They confirm the underlying physics. They validate the equations. They prove that the vacuum can be made to produce matter under extreme conditions. The full Schwinger effect remains a prediction, but it is a prediction backed by the most thoroughly confirmed theory in the history of physics. Doubting it would be like doubting that water boils at 100 degrees Celsius, simply because you have never personally turned the stove up that high. So here is where we stand at the end of this first mechanism. The vacuum is not empty. It is a dense, energetic, pressurized medium filled with virtual particle-antiparticle pairs that flicker at the edge of existence. Under normal conditions, these pairs are harmless. They appear and vanish too quickly to matter. But under extreme conditions, when a sufficiently powerful field is applied, the vacuum breaks. The virtual becomes real. Matter is pulled out of nothing. Energy is extracted from the fields and converted into tangible, measurable particles. This is not a theoretical curiosity. This is the foundational warning. It is the first crack in the illusion that empty space is passive. The Schwinger Effect tells us that the void has a threshold, a breaking point, a critical stress beyond which it cannot hold itself together. And nature has already crossed that threshold. Magnetars do it regularly. The early universe, with its unimaginable energy densities, almost certainly did it on a cosmic scale. And we, with our petawatt lasers and our insatiable curiosity, are building machines designed to do it deliberately. The question is not whether the vacuum can break. Schwinger answered that in 1951. The question is what else the vacuum is hiding. Because if empty space can be forced to produce matter under electromagnetic stress, what happens under gravitational stress? What happens when the vacuum is not just pushed, but curved, stretched, torn by the warping of space-time itself? What happens at the edge of a black hole, where gravity is so extreme that not even light can escape? The Schwinger Effect is the first domino. It establishes the principle. The vacuum is not safe. The vacuum is not stable. The vacuum is a loaded system held in check by the weakness of the fields around you. And the fields around you are weak only by accident, only because you happen to live in a quiet corner of a violent universe. The next mechanism will show you that even without reaching the Schwinger limit, even in the gentle everyday conditions of ordinary physics, the vacuum is still responding, still adjusting, still participating. It is not just that the vacuum can break under extreme stress. It is that the vacuum is always bending, always polarizing, always shifting the rules of reality in subtle, measurable ways that most people never notice. The emptiness is not watching passively. It is breathing, and you are inside it. The Schwinger Effect showed you the catastrophe. It showed you what happens when the vacuum breaks, when the stress is so extreme that empty space tears open and bleeds matter into the world. That was the violent version, the loud version, the version with magnetars and petawatt lasers, and cascading avalanches of freshly born particles. But violence is not the only way the vacuum betrays its true nature. There is a quieter betrayal, one that is happening right now, everywhere, at all times, in every atom of your body, and every photon of light that has ever crossed the universe. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It does not require astronomical field strengths. It does not require extreme conditions. It requires only that something exists. A single charged particle. A lone electron sitting in otherwise empty space. That is enough. Because the vacuum does not just break under pressure, it bends under presence. And it has been bending around you since the moment you were born. To understand this, we need to go back to those virtual particles from part 1. Remember, the vacuum is a churning sea of particle-antiparticle pairs that flicker into existence and annihilate in unimaginably short timescales. Under normal conditions, this process is symmetric. Virtual electrons and virtual positrons appear together, exist for a fleeting instant, and disappear together. On average, the vacuum looks neutral, it looks calm, it looks empty, but that average is a lie. It is a statistical average, and it hides a storm of activity underneath. Now, drop a real electron into this sea, an actual, permanent, negatively charged electron sitting in the vacuum. What happens? The electron's electric field radiates outward in all directions. It fills the surrounding space with a negative influence, and the virtual pairs in the vacuum respond. They are not inert, they are not decorative, they are charged. The virtual electron in each pair is repelled by the real electron. The virtual positron in each pair is attracted. So each virtual pair, in the fleeting instant of its existence, stretches. It orients itself. The virtual positron drifts slightly toward the real electron, and the virtual electron drifts slightly away. This is vacuum polarization. The vacuum is being polarized by the presence of the charge in exactly the same way that a dielectric material polarizes around a charged object embedded inside it. The virtual pairs are acting like tiny molecular dipoles, aligning themselves in the field of the real electron, partially cancelling its charge at a distance. Think about that carefully. You have a single electron. It has a charge, a fundamental, supposedly fixed, supposedly intrinsic property of nature. The charge of the electron is one of the most precisely measured quantities in all of physics. It appears in every equation, every circuit diagram, every chemistry textbook. We treat it as a constant. We tattoo it into our models, but vacuum polarization tells us that what we measure as the electron's charge is not the bare charge of the electron. It is the screened charge, the dress charge, the charge you see after the vacuum has wrapped itself around the electron and partially hidden it from view. Imagine trying to see a light source at the bottom of a swimming pool. The water bends and scatters the light. The brightness you see at the surface is not the true brightness of the source, it is the brightness after the water has interfered. You would have to drain the pool to see the real thing. Vacuum polarization means the vacuum is the pool, and we can never drain it. We live inside it. We measure inside it. Every instrument we build, every ruler, every clock, every detector is immersed in the same quantum sea. We have never seen a bare electron. We have never measured the true undress charge. What we call the charge of the electron is already the result of an infinite number of virtual pairs crowding around the real electron and diluting its influence. This is not a small effect, philosophically speaking. It is a fundamental redefinition of what a constant of nature actually means. The fine structure constant, alpha, which governs the strength of the electromagnetic interaction and sits at approximately 1 divided by 137, is not a number that was stamped into the universe at the beginning of time. It is a running constant. It changes depending on the energy at which you probe it. At low energies, when you observe the electron from far away, the cloud of virtual pairs is thick. The screening is strong. The effective charge looks small. But at high energies, when you slam particles together with enough violence to probe inside the cloud, you see past the screening. The effective charge grows. The fine structure constant increases. At the energy scales probed by the Large Electron-Positron Collider at CERN, roughly 91 billion electron volts, corresponding to the mass of the Z boson, the fine structure constant rises to approximately 1 divided by 128. The constant is not constant. It is a function of how closely you look. This phenomenon is called the running of the coupling constant, and it is one of the most precisely confirmed predictions in the history of particle physics. It is not an approximation. It is not an artifact of our instruments. It is a direct, measurable consequence of the vacuum being an active medium rather than an empty stage. The vacuum participates. The vacuum adjusts. The vacuum modifies the strength of every force in the universe, depending on the scale at which you examine it. And this is where the story starts to become personal, because vacuum polarization does not just alter abstract coupling constants at particle collider energies. It alters the atoms in your body. It shifts the energy levels of the simplest atom in the universe, hydrogen, in a way that was entirely unexpected, and that led to one of the most important experimental discoveries of the 20th century. In 1947, Willis Lamb and Robert Rutherford performed an experiment at Columbia University that shattered the existing theory of the hydrogen atom. According to the Dirac equation, which was the gold standard of quantum mechanics at the time, two particular energy levels of hydrogen, the 2s1/2 state and the 2p1/2 state, should have been exactly the same, identical, degenerate, in the language of physics. But Lamb and Rutherford, using microwave spectroscopy with extraordinary precision, found that these two levels were not the same. The 2s1/2 level was shifted upward by approximately 1,057 MHz relative to the 2p1/2 level. This tiny discrepancy, now known as the Lamb shift, was a crack in the foundation of theoretical physics. The Dirac equation could not explain it. No classical modification could account for it. The only explanation came from the vacuum itself. The Lamb shift arises because the electron in a hydrogen atom is not orbiting the nucleus in clean, pristine emptiness. It is orbiting inside the quantum vacuum, and the virtual particles in that vacuum are constantly interfering. Vacuum polarization is one of the contributing effects. The cloud of virtual electron-positron pairs surrounding the nucleus slightly alters the electric potential that the orbiting electron experiences. It modifies the Coulomb field of the proton. The modification is distance-dependent, and it affects the S states, where the electron has a non-zero probability of being found at the nucleus, differently from the P states, where it does not. The result is a shift, a tiny, measurable, undeniable shift that proves the vacuum is not a spectator. It is a participant in the internal structure of every atom. But vacuum polarization is not the only vacuum effect contributing to the Lamb shift. The dominant contribution comes from a related phenomenon called electron self-energy, in which the electron emits and reabsorbs virtual photons, effectively jittering around its average position due to its interaction with the electromagnetic vacuum. This jittering, sometimes called Zitterbewegung in a related context, smears out the electron's position. It means the electron is not a point sitting precisely in its orbital. It is a fuzzy cloud of probable positions, bounced around by the vacuum fluctuations like a boat on choppy water. The combination of vacuum polarization and self-energy effects produces the Lamb shift with extraordinary precision, and the agreement between theory and experiment is astonishing. The theoretical prediction, calculated using the full machinery of quantum electrodynamics with higher order corrections, matches the experimental measurement to better than 1 part in a million. This is one of the crowning achievements of QED and one of the most impressive agreements between a theoretical prediction and an experimental result in the history of science. It proves, beyond any reasonable doubt, that the vacuum is real, that the virtual particles are not mathematical fictions, that the fluctuations are not bookkeeping tricks. They are physical. They have consequences. They move atoms. Now, let us push even further. Vacuum polarization does not just shift energy levels in hydrogen. It alters one of the most fundamental properties of the electron itself, its magnetic moment. Every electron behaves like a tiny magnet. It has a magnetic moment that arises from its intrinsic spin. If electrons were simple, classical objects, this magnetic moment would have a clean, predictable value determined by the Dirac equation. The ratio of the electron's actual magnetic moment to this predicted value is called the G factor, and Dirac's theory predicts it should be exactly 2. But it is not. The measured value is slightly more than 2. Specifically, it is approximately 2.002319304. That tiny excess, the anomalous magnetic moment, is one of the most precisely measured quantities in all of experimental physics. Where does the anomaly come from? It comes from the vacuum. The electron does not exist in isolation. It is constantly interacting with the virtual particles around it. It emits virtual photons, which split into virtual electron-positron pairs, which emit more virtual photons, in a cascading hierarchy of quantum corrections. Each of these interactions slightly modifies the electron's effective magnetic moment. Vacuum polarization is one category of these corrections. The virtual pairs surrounding the electron alter the way it couples to external magnetic fields, nudging the G factor away from Dirac's clean prediction. The theoretical calculation of the anomalous magnetic moment is one of the most complex and painstaking computations in the history of physics. It requires summing Feynman diagrams to the 10th order in perturbation theory. That means accounting for virtual processes involving up to 5 virtual photons and the corresponding virtual pairs. The number of individual diagrams at that order exceeds 12,000. Each one must be calculated, many requiring sophisticated numerical integration techniques and years of computational effort. The result, when all diagrams are summed, agrees with the experimental measurement of more than 10 significant figures. 10 decimal places. This is the most accurate prediction in all of science. Nothing else in physics, chemistry, or any other discipline comes close, and this prediction depends critically on vacuum polarization. Without the contribution of the virtual pairs, the number is wrong. Without acknowledging that the vacuum is an active, responsive medium that modifies the properties of every particle embedded within it, the most precise measurement in human history cannot be explained. The vacuum is not a footnote, it is the explanation. Let us step back and consider what this means for the story we are telling. In part 1, we established that the vacuum can break. The Schwinger Effect showed us that under extreme conditions, the boundary between existence and non-existence is not absolute. It can be crossed. The vacuum can be forced to produce real matter. That was a catastrophic instability, a threshold event, a breaking point. But vacuum polarization reveals something more insidious. It reveals that you do not need extreme conditions to see the vacuum's influence. You do not need magnetars or petawatt lasers. You just need an electron. One electron sitting in space, and the vacuum wraps itself around that electron like a cocoon. It screens its charge, it shifts its energy levels, it alters its magnetic moment, it modifies the way it interacts with every other particle in the universe. And it does this continuously, persistently, universally. There is no region of the cosmos where this is not happening. There is no particle that escapes it. The vacuum is not waiting for a catastrophe to act. It is acting right now, in every atom, at every moment. This transforms the vacuum from a passive container into an active medium, and that transformation has consequences that go far beyond the electron. Consider the photon, light, the carrier of the electromagnetic force. In classical physics, light travels through empty space in a perfectly straight line at a perfectly constant speed. Two beams of light that cross paths do not interact. They pass through each other like ghosts. This is because photons are electrically neutral and do not couple directly to each other in classical electrodynamics. But vacuum polarization changes this. When a photon travels through the vacuum, it can temporarily convert into a virtual electron-positron pair. That pair exists for a fleeting instant, and during that instant, it can interact with another photon that also happens to be converting into a virtual pair. The two photons, which should be invisible to each other, communicate through the vacuum. They exchange influence through the medium of virtual particles. This phenomenon is called light-by-light scattering. It is extraordinarily rare. The probability is suppressed by 4 powers of the fine structure constant, making it roughly 1 billion times less likely than ordinary electron-photon scattering. But it is real. In 2017, the ATLAS experiment at CERN announced the first direct observation of light-by-light scattering in ultra-peripheral heavy ion collisions. Two photons, traveling through what we would naively call empty space, bounced off each other. They interacted, they deflected. Not because they touched. Not because they collided with matter, but because the vacuum between them was not empty. The vacuum provided the medium through which the interaction occurred. This is a profound result. It tells us that even light, the most fundamental carrier of information in the universe, does not travel through a void. It travels through a medium that bends its path, alters its polarization, and under extreme conditions can even split it or slow it down. In extremely strong magnetic fields, vacuum polarization causes birefringence, a splitting of light into two polarization states that travel at slightly different speeds. This vacuum birefringence has been predicted since the 1930s by Hans Euler and Werner Heisenberg, and there is active observational effort to detect it in the light from neutron stars. The vacuum is not just modifying particles, it is modifying light itself. It is modifying the medium through which all information in the universe travels. Now, let us widen the lens even further. Vacuum polarization in quantum electrodynamics is just one instance of a broader phenomenon. The same mechanism operates in quantum chromodynamics, the theory of the strong nuclear force. In QCD, the vacuum is filled with virtual quark-antiquark pairs and virtual gluons. These virtual particles screen and anti-screen the color charge of quarks in a way that is even more dramatic than the electromagnetic case. In QED, the running of the coupling constant means the electromagnetic force gets stronger at short distances. In QCD, the opposite happens. The strong force gets weaker at short distances, a phenomenon called asymptotic freedom, discovered by David Gross, Frank Wilczek, and David Politzer, for which they received the Nobel Prize in 2004. At very short distances, Quarks behave almost as free particles. But at larger distances, the QCD vacuum asserts itself with terrifying force, confining quarks inside protons and neutrons with a binding energy so fierce that you can never isolate a single quark. The QCD vacuum is not just an active medium, it is a prison. The vacuum polarization of the strong force also generates most of the mass in the visible universe. The quarks inside a proton have a combined bare mass of only about 9 million electron volts. But a proton has a mass of approximately 938 million electron volts. Where does the rest come from? It comes from the vacuum. It comes from the energy of the gluon fields and the virtual quark-antiquark pairs that churn inside the proton. The mass of your body, the mass of the Earth, the mass of the Sun, nearly all of it is not the mass of fundamental particles. It is the mass of the vacuum interactions binding those particles together. You are made of vacuum energy. You are made of the consequence of quantum fields fluctuating around confined quarks. Your weight on a bathroom scale is overwhelmingly a measurement of the energy of empty space trapped inside your atoms. Sit with that for a moment. Every time you lift a heavy object, you are fighting the vacuum. Every time your feet press against the floor, the resistance you feel is not the resistance of matter against matter. It is the resistance of vacuum energy packed into an impossibly small volume. The floor does not push back because it is solid. It pushes back because the quantum fields inside its atoms are in a state of enormous internal tension, a tension maintained by the vacuum itself. This is the deeper message of vacuum polarization. The Schwinger Effect told you the vacuum can break. Vacuum polarization tells you the vacuum is already working. It is already bending, already screening, already modifying every charge, every force, every interaction in the universe. The constants of nature that we print in textbooks are not fixed numbers. They are emergent values. They are the net result of a perpetual negotiation between bare particles and the vacuum that surrounds them. Change the vacuum, and you change the constants. Change the constants, and you change chemistry, biology, gravity, light, everything. And here is the part that connects back to the central terror of this story. If the vacuum state were to change, if the quantum fields were to settle into a different configuration with different fluctuation properties, then the screening would change. The effective charges would change. The running of the coupling constants would follow different curves. The masses of particles generated by vacuum interactions would shift. Atoms as we know them would cease to exist. Not because the particles were destroyed, but because the medium in which they exist altered its character. It would be like changing the refractive index of the ocean. The fish would not be killed by a bullet. They would be killed because the water they breathed became something else entirely. The vacuum is not just the environment in which physics happens. The vacuum is physics. It defines the strength of forces. It determines the masses of particles. It sets the rules of chemistry, biology, and structure. Without it, there are no atoms, no molecules, no stars, no life. Every property of the universe that you consider fundamental is, in truth, a property of the vacuum state. And the vacuum state, as we have already begun to see, is not guaranteed to be permanent. We start with the Schwinger Effect, the catastrophic tearing of the vacuum under extreme force. Now we have seen vacuum polarization, the quiet, ubiquitous bending of the vacuum around every particle in existence. These are not two separate phenomena. They are two expressions of the same underlying reality. The vacuum is a dynamic, responsive, energetic medium. Under extreme stress, it breaks. Under ordinary conditions, it bends. In both cases, it is active. In both cases, it participates. In both cases, it proves that what we call empty space is the most important substance in the universe. But so far, we have been dealing with electromagnetic and chromodynamic fields. We have seen what happens when the vacuum interacts with electric charges and color charges. There is another force in the universe. one that does not merely distort the vacuum, one that warps the very geometry of space-time itself. And when gravity enters the picture, when the curvature of space-time becomes extreme enough, the vacuum does something even more extraordinary than bleeding matter or bending light. It creates particles at the boundary of oblivion. It radiates from the edge of a black hole, and in doing so, it suggests that the connection between gravity, quantum mechanics, and the vacuum is far deeper and far more dangerous than anyone initially suspected. The vacuum does not just respond to fields, it responds to the shape of the universe itself. And when that shape becomes extreme enough, the vacuum does not bend. It does not break, it evaporates. We have now seen the vacuum break under electromagnetic force and bend under the presence of ordinary charged particles. Both mechanisms reveal the same underlying truth. Empty space is not empty. It is a pressurized, responsive, dynamic medium that participates in every physical process in the universe. But so far, the forces involved have been familiar. Electric fields, magnetic fields, the strong nuclear force. These are forces we can generate in laboratories. Forces we can measure with instruments on a table. They operate within space-time. They push and pull objects that move through the fabric of the cosmos. Now we turn to something fundamentally different. We turn to a force that does not operate within space-time. It operates on space-time. It bends the stage itself. It warps the geometry of the arena in which everything else happens. We are talking about gravity. And when gravity becomes extreme enough, when the curvature of space-time reaches the breaking point, the vacuum does not merely bleed electrons and positrons. It does something far more profound. It radiates. It glows. It emits a steady stream of real particles from a region where nothing should be able to escape. It does this at the boundary of the most extreme gravitational object in the universe, the event horizon of a black hole. This phenomenon is called Hawking radiation, and it is not simply a quirky property of black holes. It is the most dramatic demonstration that the vacuum, space-time, and the very concept of existence are entangled in ways that threaten the foundations of physics. To understand Hawking radiation, we have to understand what a black hole actually does to space. Forget the popular image of a cosmic drain sucking things in. That metaphor is useful for visualization, but useless for physics. A black hole is not a hole. It is a region of space-time where the curvature has become so extreme that the geometry itself folds over. The event horizon is not a surface. It is not a wall. It is a boundary in the causal structure of the universe. Inside the horizon, all paths through space-time, including the path of light, curve inward toward the singularity. There is no trajectory, no speed, no trick of physics that allows anything to travel outward. The horizon is not a barrier that blocks your escape. It is the point beyond which the concept of escape ceases to have meaning. The future itself points inward. Now, place this monstrous geometric structure into the quantum vacuum. The vacuum, as we have established, is a sea of virtual pairs in constant flux. In flat space-time, far from any gravitational source, the energy books balance. Every pair that forms is immediately reclaimed. The vacuum remains in its ground state. Nothing measurable happens. But near the event horizon of a black hole, the geometry of space-time is violently curved. And this curvature does something terrible to the virtual pairs. The original picture, as Stephen Hawking described in his landmark 1974 paper published in the journal Nature, uses a simplified but powerful visualization. A virtual pair is created just outside the event horizon. One particle has positive energy, the other has negative energy. In flat space-time, they would recombine almost instantly. But the extreme tidal forces near the horizon can separate them before they annihilate. The negative energy particle falls through the horizon into the black hole. The positive energy particle escapes to infinity as real radiation. From the perspective of a distant observer, the black hole has emitted a particle. It has radiated. And because the infalling particle carried negative energy, The black hole has lost a corresponding amount of mass. The black hole shrinks, it evaporates. Given enough time, it disappears entirely. This intuitive picture, while useful, is not quite what happens at the mathematical level. The rigorous derivation of Hawking radiation does not depend on following individual virtual particles. It depends on something deeper. It depends on the fact that the concept of a particle itself is ambiguous in curved spacetime. In flat spacetime, there is a natural and unambiguous way to define what a particle is. You decompose the quantum field into positive frequency modes and negative frequency modes. Positive frequency modes correspond to particles. Negative frequency modes correspond to antiparticles. The vacuum is the state with no positive frequency excitations. This decomposition is universal. Every observer in flat spacetime agrees on which modes are positive frequency and which are negative. They all agree on the particle content of any given state. They all agree on what empty means, but in curved spacetime, this agreement breaks down. The natural modes of the quantum field depend on the geometry of spacetime, and different regions of spacetime have different geometries. Near the event horizon of a black hole, the geometry is radically different from the geometry far away. An observer falling freely through the horizon would decompose the field into one set of modes. An observer hovering far from the black hole would decompose the field into a completely different set. And these two decompositions do not agree. This is the mathematical core of Hawking radiation. What the infalling observer calls the vacuum state, the state with no particles, does not look like a vacuum to the distant observer. The distant observer, using their own natural mode decomposition, sees that state as containing a thermal bath of real particles. Particles with real energy, real momentum, real measurable properties. The distant observer sees radiation streaming outward from the vicinity of the black hole. The infalling observer sees nothing. The same quantum state is simultaneously empty and full. The particle content of the universe depends on who is asking. This is not a disagreement about interpretation. It is not a matter of one observer being right and the other being wrong. Both descriptions are mathematically valid. Both are physical. The vacuum state, as defined by the infalling observer, genuinely contains no particles in that observer's frame, but it genuinely contains particles in the distant observer's frame. The universe does not have a fixed inventory of particles. The inventory depends on the geometry and the observer. Hawking calculated the spectrum of this radiation and found something remarkable. The radiation is thermal. It has the same statistical distribution as radiation from a hot object, a black body. The temperature of this radiation, now called the Hawking temperature, is inversely proportional to the mass of the black hole. For a black hole with the mass of our Sun, the Hawking temperature is approximately 60 billionths of a Kelvin. That is unimaginably cold, far colder than the cosmic microwave background radiation, which sits at about 2.7 Kelvin. This means that stellar mass black holes are currently absorbing more energy from the cosmic background than they emit via Hawking radiation. They are growing, not shrinking. The evaporation is overwhelmed by the influx, but the equation cuts both ways. Smaller black holes are hotter, much hotter. A black hole with the mass of a mountain, roughly 1 trillion kilograms, would have a Hawking temperature of over 100 billion Kelvin, hotter than the core of a collapsing star. And as the black hole radiates, it loses mass. As it loses mass, it gets hotter. As it gets hotter, it radiates faster. This is a runaway process, a positive feedback loop. The evaporation accelerates. In the final moments of a black hole's life, the temperature skyrockets, the radiation output becomes enormous, and the black hole explodes in a burst of high-energy particles and gamma rays. The final evaporation of a small black hole would release energy equivalent to millions of nuclear warheads, detonating simultaneously, and then it would be gone. The singularity, the event horizon, the trapped region of spacetime, all of it would vanish. The black hole would have converted its entire mass into radiation, particle by particle, extracted from the vacuum at the edge of its own horizon. This is vacuum particle creation at its most extreme. The gravitational field of the black hole, encoded in the curvature of space-time, performs the same fundamental trick as the Schwinger effect. It takes virtual pairs and promotes them to real pairs. It extracts matter and energy from the quantum vacuum. But instead of using an electric field to rip apart electron-positron pairs, it uses the geometry of space-time itself. The curvature near the horizon plays the role of the external field. The tidal stretching of space-time plays the role of the force that separates the pair. The mechanism is different in detail, but identical in principle. The vacuum has a breaking point, and gravity can reach it. This connection between the Schwinger effect and Hawking radiation is not superficial. It has been formalized mathematically. In the 1970s, William Unruh, Bryce DeWitt, and others showed that the rate of particle creation near a black hole can be understood using the same mathematical tools developed for the Schwinger effect in quantum electrodynamics. The surface gravity of the black hole, which measures the strength of the gravitational field at the horizon, plays the same role as the electric field strength in Schwinger's formula. The exponential suppression factor has the same structure. The physics is unified. The vacuum responds to stress, regardless of whether that stress is electromagnetic or gravitational. But Hawking radiation introduces something the Schwinger effect does not. It introduces a crisis of information. This is the black hole information paradox, and it strikes at the heart of quantum mechanics. Here is the problem. Quantum mechanics is built on a principle called unitarity. Unitarity means that information is conserved. If you know the complete quantum state of a system at one time, you can in principle calculate its complete quantum state at any other time, past or future. Information is never created and never destroyed. It can be scrambled, encrypted, and hidden, but it cannot be erased. This is not a minor rule. It is the foundational axiom of quantum theory. Without unitarity, quantum mechanics collapses. Probabilities stop adding up to 1. Predictions become impossible. Now consider what happens when a black hole evaporates. Objects fall into the black hole. They carry information with them. The quantum states of every particle that crosses the horizon are encoded in the infalling matter. The black hole grows, absorbing the information. Then Hawking radiation begins. Particle by particle, the black hole shrinks. The radiation it emits is thermal. Thermal radiation, by definition, carries no detailed information about the source. It is random, it is statistical, it is the same regardless of what fell in. A black hole that swallowed a library emits the same thermal spectrum as a black hole that swallowed a cloud of hydrogen gas. So when the black hole finally evaporates completely, when the last burst of radiation dissipates into the cosmos, where is the information? It went in with the matter. It did not come out with the radiation. The black hole is gone. The information appears to have been destroyed. If this is true, unitarity is violated. Quantum mechanics is broken. The most fundamental law of quantum theory has been overruled by gravity. Hawking himself initially argued that this was the correct conclusion. He proposed that black holes destroy information, and that quantum mechanics needs to be modified in the presence of strong gravity. This was an extraordinary claim. It meant that the two pillars of modern physics, quantum mechanics and general relativity, were not just difficult to unify. They were fundamentally incompatible. One of them had to give. The theoretical community split. For decades, this paradox fueled one of the most intense debates in the history of physics. On one side, Hawking and those who believed gravity wins. Information is lost. Unitarity fails. On the other side, Leonard Susskind, Gerhard Hooft, Juan Maldacena, and those who believed quantum mechanics wins. Information must be preserved somehow, even if we do not understand how. The resolution, or at least the leading candidate for resolution, came from an unexpected direction. It came from the holographic principle and the ADS/CFT correspondence, a mathematical framework developed by Maldacena in 1997 that establishes an exact equivalence between a theory of gravity in a higher dimensional space and a quantum theory without gravity on its boundary. In this framework, everything that happens inside a volume of space, including the formation and evaporation of black holes, is exactly encoded on the boundary of that space. The information is not inside the black hole, it is on the horizon. It is smeared across the two-dimensional surface like ink on the wall of a room. If this is correct, then Hawking radiation is not truly thermal. It appears thermal to a distant observer who cannot access the detailed correlations hidden in the radiation. But those correlations are there, encoded in subtle quantum entanglement between the emitted particles. The information comes out, but it comes out scrambled so thoroughly that it looks random. It is the ultimate encryption. The key to decoding it would require capturing every single photon and particle emitted over the entire lifetime of the black hole and performing a computation of incomprehensible complexity. Hawking himself eventually conceded this point, famously paying off a bet with John Preskill in 2004 by giving him a baseball encyclopedia, a symbolic gesture acknowledging that information is indeed preserved. But the concession did not resolve the paradox. It deepened it. Because if the information is encoded on the horizon, and the horizon is a feature of space-time geometry, then the vacuum at the horizon is doing something extraordinary. It is not just creating particles, it is encoding information. It is transferring the quantum state of everything that ever fell into the black hole into the correlations of the outgoing radiation. The vacuum at the event horizon is not a simple source of thermal noise. It is a quantum information processor of unimaginable power and complexity. This revelation transforms our understanding of what the vacuum is capable of. In part 1, the vacuum was a pressurized vessel that could be forced to release particles. In part 2, the vacuum was a responsive medium that screened charges and modified forces. Now, in part 3, the vacuum is something more. It is an information channel. It is a bridge between the interior of a black hole and the exterior universe. It is the mechanism by which the universe maintains its own logical consistency in the face of gravitational catastrophe. The vacuum is not just dynamic, it is computational. And the implications reach far beyond black holes. The connection between vacuum particle creation and information has led physicists to suspect that the same principles apply to the universe as a whole. The event horizon of a black hole is not the only horizon in physics. The observable universe has a cosmological horizon, a boundary beyond which light has not had time to reach us since the Big Bang. In an accelerating universe driven by dark energy, this cosmological horizon behaves in some ways like the horizon of a black hole. It has a temperature. It radiates. The vacuum at the cosmological horizon produces particles through the same mechanism as Hawking radiation. This is called Gibbons-Hawking radiation, named after Gary Gibbons and Stephen Hawking, who derived it in 1977. The temperature of this cosmological radiation is extraordinarily small. It is proportional to the Hubble constant and comes out to roughly 10 to the minus 30 Kelvin. A number so tiny that it is far below any conceivable detection threshold. But the principle is the same. Wherever there is a horizon, wherever the causal structure of space-time is disrupted, the vacuum responds by creating particles. Horizons are vacuum-breaking machines. They are the geometric equivalent of the Schwinger limit. The curvature of space-time near a horizon plays the same role as the critical electric field. The vacuum does not care whether the stress comes from electromagnetism or from the shape of the universe itself. It responds the same way. It creates. It radiates. It transforms nothing into something. This is the thread that connects all three mechanisms we have examined so far. The Schwinger Effect uses electromagnetic fields. Vacuum polarization uses the passive presence of charges. Hawking radiation uses space-time curvature. But in every case, the underlying story is the same. The vacuum is not stable in any absolute sense. It is conditionally stable. It remains calm only when the conditions are gentle. Push it electromagnetically, and it bleeds matter. Curve it gravitationally, and it radiates particles. Let a charge simply exist in its midst, and it bends around it, distorting forces, shifting constants, modifying the rules. And now we must confront the most disturbing implication of Hawking radiation. It is not just that gravity can create particles from the vacuum. It is that this particle creation is observer-dependent. The infalling observer sees no radiation. The distant observer sees a thermal bath. The particle content of the universe is not an objective fact. It depends on who is measuring and how they are moving through space-time. This cracks open a door that most physicists would prefer to keep shut. Because if the number of particles in the universe depends on the observer, then the most basic inventory of reality, the list of things that exist, is not fixed. It is negotiated. It is relative. It is subjective in a physical, measurable, non-philosophical sense. The Schwinger Effect showed us the vacuum can be broken. Vacuum polarization showed us the vacuum is always active. Hawking radiation shows us the vacuum's behavior depends on the shape of space-time and the state of the observer. Each mechanism deepens the instability. Each mechanism removes another layer of the illusion that empty space is safe, static, and universal. But there is one more step. One more mechanism that takes this observer dependence and strips it of all astronomical context. You do not need a black hole. You do not need an event horizon. You do not need any gravitational source at all. The next effect demonstrates that the vacuum's instability can be triggered by something far more mundane, far more personal, far more terrifying in its implications. All you need to do is accelerate, push yourself through space, feel the force against your body, and the vacuum around you begins to glow. Not because anything has changed about the vacuum, but because something has changed about you. Your motion through space-time has altered the definition of emptiness. What was a cold, dead, silent void to a stationary observer becomes a warm bath of real, detectable particles to an accelerating one. The vacuum is not just unstable under extreme forces and extreme curvatures. It is unstable under a change of perspective. And that instability is not waiting at the edge of a black hole billions of light years away. It is waiting for anyone who dares to move. At the end of the last section, we stood at the event horizon of a black hole and watched the vacuum perform an act of creation. Hawking radiation showed us that the extreme curvature of space-time near a black hole tears virtual pairs apart and promotes them to real particles. A distant observer sees thermal radiation streaming outward from the horizon. An infalling observer sees nothing. The particle content of the universe, the raw inventory of what exists, turned out to depend on who is asking and where they are standing. That was disturbing enough. But at least you could comfort yourself with the thought that this phenomenon requires a black hole. Black holes are exotic. They are rare. The nearest known stellar mass black hole is over 1,000 light years away. You could tell yourself that observer-dependent reality is a quirk of extreme gravity, an edge case that does not apply to your everyday life. A problem for astrophysicists to worry about while you go about your business in the gentle, flat, well-behaved space-time of your living room. That comfort is about to be taken from you. In 1976, 2 years after Hawking published his landmark paper on black hole radiation, a Canadian physicist named William George Unruh published a result that extended Hawking's insight into terrifyingly mundane territory. Unruh showed that you do not need a black hole to see particles emerge from the vacuum. You do not need extreme space-time curvature. You do not need any gravitational source at all. You just need to accelerate. If you strap yourself to a rocket and accelerate through the vacuum of empty space at a constant rate, the vacuum around you will not appear empty. It will appear to be filled with a warm bath of thermal radiation. Real particles, detectable particles, particles with a temperature that is directly proportional to your acceleration. This is the Unruh Effect, and it is not a correction to Hawking radiation. It is not a footnote. It is the deeper principle from which Hawking radiation itself can be derived. Let us set up the scenario precisely. Imagine two observers in otherwise identical conditions. The first observer is floating freely in deep space, far from any gravitational source, in perfect inertial motion. No forces act on this observer. They drift through the cosmos in a straight line at constant velocity. This observer carries a perfect particle detector, the most sensitive device ever conceived. They point it at the surrounding vacuum and they wait. They detect nothing. Absolute zero. Perfect silence. The vacuum is in its ground state. There are no real particles anywhere. The quantum fields are in their lowest energy configuration, fluctuating only with the inevitable zero-point jitter of virtual pairs that annihilate too quickly to register. This is what empty means in quantum field theory. This observer confirms it. The void is void. Now, the second observer is in the same region of space, the same vacuum, the same quantum fields, the same zero-point fluctuations, but this observer is accelerating. They are strapped to a rocket engine that pushes them with a constant proper acceleration. They feel a force pressing them into their seat. They carry an identical particle detector. They point it at the same vacuum, and they detect particles, not virtual particles, real ones. Particles with real energy that click in the detector, deposit heat, and increase the reading on a thermometer. The detector registers a thermal spectrum, a bath of radiation that looks exactly like the radiation from a hot object. The temperature of this radiation is given by a simple and elegant formula. The Unruh temperature equals the acceleration multiplied by the reduced Planck constant, divided by 2 pi times the speed of light times Boltzmann's constant. In natural units, the relationship is even starker. Temperature is proportional to acceleration. Full stop. The faster you accelerate, the hotter the vacuum appears. Two observers. Same vacuum, same region of space, same quantum fields. One sees nothing, the other sees a thermal bath of particles, and both are correct. Neither is hallucinating, neither is making an error. The physics is perfectly consistent. The quantum state of the field is the same for both. But the definition of particle is different. The concept of emptiness is different. What counts as the vacuum depends on how you move through space-time. This is the Unruh effect in its purest form. And it is deeply, fundamentally unsettling, because it tells us that the most basic question you can ask about the universe, what is here, does not have a single answer. The answer depends on your state of motion. It depends on the trajectory you trace through space-time. It depends on you. Let us examine why this happens at the mathematical level. In quantum field theory, particles are defined as excitations above the vacuum state. The vacuum state is defined as the lowest energy state of the quantum field, as perceived by a particular class of observers. In flat spacetime for inertial observers, there is a unique and natural vacuum state called the Minkowski vacuum. All inertial observers agree on this vacuum. They all see the same empty space. They all count the same number of particles, which is 0. But an accelerating observer does not use the same coordinates as an inertial observer. An accelerating observer experiences a different geometry of spacetime. Specifically, a uniformly accelerating observer in flat spacetime can be described using a set of coordinates called Rindler coordinates. In Rindler coordinates, the spacetime accessible to the accelerating observer is not the full Minkowski spacetime. It is only a wedge-shaped region called the Rindler wedge. The boundary of this wedge is a surface called the Rindler horizon. It is a horizon in the same causal sense as the event horizon of a black hole. There are regions of space-time from which signals can never reach the accelerating observer, no matter how long they wait. Information is lost beyond the Rindler horizon, just as information is lost beyond a black hole's event horizon. And here is the critical point. The natural vacuum state, as defined by the accelerating observer in Rindler coordinates, is not the same as the Minkowski vacuum. When you express the Minkowski vacuum in terms of the Rindler observer's particle modes, you find that it contains particles. Specifically, it contains a thermal distribution of particles at the Unruh temperature. The Minkowski vacuum, which is perfectly empty according to inertial observers, is a warm thermal bath according to accelerating observers. This is not an illusion. It is not a coordinate artifact. The accelerating observer's detector genuinely clicks. It genuinely absorbs energy. It genuinely heats up. The energy comes from the work done by whatever force is maintaining the acceleration. The rocket engine burns fuel. That fuel provides the energy. The vacuum channels the energy into the detector through the thermal bath of Unruh particles. The process is entirely consistent with conservation of energy. Nothing is free, nothing is magical, but the interpretation is revolutionary. The vacuum has not changed, the quantum fields have not changed. What has changed is the observer's relationship to the fields, and that change in relationship has transformed nothing into something. Now, let us connect this explicitly to what we learned in Part 3. Hawking radiation and the Unruh effect are not merely analogous. They are mathematically equivalent in a precise sense, linked by the equivalence principle of general relativity. Einstein's equivalence principle states that a uniform gravitational field is locally indistinguishable from a constant acceleration. If you're standing in a closed room and you feel a force pulling you toward the floor, you cannot tell from local measurements alone whether that force is caused by the gravity of a planet beneath you or by a rocket engine accelerating the room upward. The physics inside the room is identical in both cases. This is not an approximation. It is a foundational axiom of general relativity. Apply this principle to the vacuum. An observer hovering at a fixed distance above a black hole's event horizon must accelerate constantly to avoid falling in. They fire their rockets. They feel a force. They are not in free fall. They are in exactly the same physical situation as an accelerating observer in flat space-time. And according to the Unruh effect, they should see a thermal bath of particles. Hawking showed that they do. The temperature of this thermal bath, as seen by the hovering observer, is exactly the Unruh temperature corresponding to their acceleration. As the observer hovers closer to the horizon, the required acceleration increases and the temperature rises. At the horizon itself, the acceleration diverges, and the temperature becomes infinite. Meanwhile, an observer in free fall through the horizon sees nothing. No particles, no radiation, no thermal bath. They are in inertial motion. They are the quantum field theory equivalent of the floating observer in flat space-time. For them, the vacuum is empty. This is the same dichotomy we saw with Hawking radiation, but now it has a clear physical explanation. The radiation is not something the black hole emits in any absolute sense. It is a consequence of the observer's acceleration. The horizon creates the acceleration, and the acceleration creates the particles. The Unruh effect is the engine. Hawking radiation is one of its applications. This unification is beautiful, but it is also alarming, because it means that observer-dependent particle creation is not limited to black holes. It is not limited to cosmological horizons. It happens whenever any observer accelerates, anywhere in the universe, for any reason. Every time you step on the gas pedal in your car, you are technically immersed in a bath of Unruh radiation. Every time you stand on the surface of the Earth, resisting gravitational freefall through the acceleration of the ground pushing up against your feet, the vacuum around you is technically warm. The reason you do not notice this is that the effect is extraordinarily small for everyday accelerations. To produce Unruh radiation with a temperature of just 1 Kelvin, you would need an acceleration of approximately 2.4 times 10 to the 20th meters per second, squared. That is roughly 25 billion times the acceleration due to gravity on Earth's surface. The Unruh temperature associated with standing on the ground is approximately 4 times 10 to the minus 20 Kelvin. That is a number so vanishingly small that no instrument ever built or imagined could detect it. It is roughly 19 orders of magnitude below the cosmic microwave background. It is functionally zero, but functionally zero is not actually zero. The effect is real. It is predicted by the same quantum field theory that gives us the Lamb shift, the anomalous magnetic moment of the electron, and the Casimir effect, all of which have been confirmed to extraordinary precision. The mathematical structure is rigorous. The derivation is airtight. The only reason the Unruh effect has not been directly observed is the practical impossibility of achieving the required accelerations in a controlled laboratory environment. That said, physicists are not giving up on detection. Several proposals exist for indirect observation. One approach involves studying the behavior of accelerating electrons in particle storage rings. An electron circulating in a synchrotron is constantly accelerating, and the Unruh effect predicts a subtle modification to its spin dynamics and radiation spectrum. Another proposal involves using ultra-intense laser fields to accelerate electrons so violently that the Unruh temperature becomes measurable. A third approach, more speculative, involves analog systems, laboratory setups using fluids or optical systems that mimic the mathematics of the Unruh effect without requiring actual acceleration to relativistic scales. But whether or not we detect it directly, the theoretical implications are already devastating. Because the Unruh effect does not merely say that the vacuum looks different to different observers. It says that the concept of a particle, the most fundamental unit of physical existence, is observer-dependent. There is no absolute observer-independent answer to the question of how many particles exist in a given region of space. The answer depends on the trajectory of the observer through spacetime. In the Minkowski vacuum, the answer is 0 for inertial observers and non-zero for accelerating observers. Both answers are physically real. Both lead to measurable consequences. Neither is more correct than the other. This shatters the naive picture of the universe as a container filled with a fixed collection of objects. We are taught to think of the universe as a vast stage containing a definite number of electrons, protons, photons, and other particles, each with a definite position and a definite state. The particle inventory exists. The universe has a parts list. But the Unruh effect tells us this is wrong. The parts list depends on the reader. A particle that exists for one observer does not exist for another. The universe does not have an objective particle content. It has observer-relative particle content. This raises a question that strikes at the philosophical core of physics. If the particle content of the universe is observer-dependent, what is objectively real? What is the invariant, frame-independent truth about the quantum fields? The answer, according to modern quantum field theory, is that the quantum state of the field is real and observer-independent. The Minkowski vacuum is a single, well-defined quantum state. That state does not change when an observer accelerates. What changes is the way the observer decomposes that state into particles. The state is invariant. The interpretation is not. This is analogous to a more familiar situation. Consider a vector, an arrow pointing in some direction in three-dimensional space. The vector itself is an objective, invariant geometric object. But the components of the vector, the numbers you use to describe it, depend on the coordinate system you choose. Rotate your axes, and the components change. The vector does not. Similarly, the quantum state of the vacuum is an invariant object. But the particle content you assign to it depends on your choice of observer, your choice of coordinate system, your choice of how to decompose the field into modes. Particles are not fundamental. Fields are fundamental. Particles are the shadows that fields cast on the walls of our particular observational framework. This is a radical demotion of particles from the center of physics. For centuries, we have built our understanding of the universe on the idea that matter is made of particles. Atoms are made of electrons, protons, and neutrons. Protons are made of quarks. Forces are mediated by exchange particles, photons, gluons, W and Z bosons. The entire standard model is formulated in the language of particles. But the Unruh effect reveals that this language is contingent. It is observer-dependent. It is not the language of ultimate reality. It is the language of a particular class of observers in a particular state of motion. Change your motion, and the dictionary changes. Now, let us bring all of this back to the central thread of our story. In part 1, the Schwinger effect showed us that the vacuum can be ripped open by sufficiently strong electromagnetic fields. The boundary between existence and non-existence is not absolute. It has a threshold, and that threshold can be crossed. In part 2, vacuum polarization showed us that the vacuum is always active, always bending around every charge, always modifying forces and constants. The vacuum is not a passive stage, it is a responsive medium. In part 3, Hawking radiation showed us that gravitational curvature can perform the same trick as electromagnetic fields, creating particles from the vacuum at the event horizon of a black hole, and that this process is observer-dependent. What the infalling observer calls empty space, the distant observer calls a thermal bath. Now, in part 4, the Unruh effect has universalized this observer dependence. It is not a special feature of black holes. It is a general property of the vacuum. The vacuum does not contain a fixed, objective inventory of particles. The inventory depends on the observer. The number of things that exist in the universe is not a fact of nature. It is a relationship between nature and the entity asking the question. Each mechanism we have examined has deepened the same fundamental instability. The vacuum is not empty. It is not passive. It is not objective. And each step has moved the instability closer to home. The Schwinger effect required fields of 10 to the 18th volts per meter. Vacuum polarization required only the presence of a single charged particle. Hawking radiation required a black hole. The Unruh effect requires only that you move. The threshold keeps dropping. The instability keeps creeping closer. And through all of this, one question has been lurking in the background. A question we have been circling without directly confronting. If the vacuum is this active, this responsive, this fragile, then how do we know that the vacuum state we currently inhabit is the right one? How do we know that our vacuum, the one that gives rise to the particular constants, forces and particle masses that allow atoms and chemistry and biology to exist, is the lowest energy state? How do we know it is the true ground state? Because if it is not, if our vacuum is merely a local minimum rather than the absolute minimum, if we are perched on a ledge rather than resting at the bottom of the valley, then everything we have learned so far is merely the preamble to a catastrophe. The Schwinger effect showed us the vacuum can bleed. Vacuum polarization showed us the vacuum can bend. Hawking radiation showed us the vacuum can radiate. The Unruh effect showed us the vacuum can change its face depending on who looks at it. But none of these mechanisms destroy the vacuum itself. They stress it, they exploit it, they reveal its hidden dynamics, but they leave the vacuum state fundamentally intact. The rules of physics survive, the constants endure, the universe continues. The final mechanism does not leave the vacuum intact. The final mechanism is the one that replaces it. Not with a modified version, not with a warmer version, not with a version that has a few extra particles, but with an entirely different vacuum state. A state with different constants, different forces, different particle masses, different rules of chemistry, biology, and structure. A state in which atoms as we know them cannot form, in which light behaves differently, in which the intricate molecular machinery of life dissolves into incoherent noise. The final mechanism is the one the vacuum has been warning us about all along. Every instability, every fluctuation, every observer-dependent shimmer was a symptom. A tremor before the earthquake. A warning that the ground beneath reality is not bedrock. It is a shelf, and the fall beneath it has no bottom that we would recognize. Every mechanism we have examined has pointed in the same direction. The Schwinger Effect revealed that the vacuum bleeds matter under electromagnetic stress. Vacuum polarization revealed that the vacuum is permanently active, bending around every charge, rewriting the effective strength of forces, generating the majority of the mass in your body through confined field energy. Hawking radiation revealed that space-time curvature can extract particles from the vacuum at gravitational horizons, and that this process entangles the vacuum with the deepest puzzles of information and quantum gravity. The Unruh Effect revealed that the very concept of a particle, the most basic unit of physical existence, is not objective. It depends on the observer. It depends on motion. Two observers in the same vacuum can disagree on whether anything exists at all, and both can be right. But in every case, the vacuum state itself survived. The fundamental rules of physics persisted. The constants endured. Chemistry still worked. Atoms still held together. Light still traveled at the same speed. The stage was shaken, but it did not collapse. Now we arrive at the mechanism that collapses the stage. To understand what is about to happen, we need to revisit the concept of energy states. This is the language that connects every branch of physics, from thermodynamics to quantum mechanics to cosmology. Every physical system seeks its lowest energy configuration. A ball rolls to the bottom of a hill. A hot cup of coffee cools to room temperature. A stretched rubber band snaps back to its relaxed shape. These are all examples of systems moving toward lower energy. The state of lowest possible energy is called the ground state, and once a system reaches it, it stays there. It is stable. It has nowhere further to fall. The vacuum of our universe is supposed to be in its ground state. The quantum fields that permeate all of space, the electron field, the quark fields, the electromagnetic field, the Higgs field, all of them are supposed to be settled into their lowest energy configuration. This is what we mean when we say the vacuum is stable. It is not just that the vacuum is empty of particles, it is that the fields themselves have found their resting place. They have rolled to the bottom of the hill, they have stopped moving, and the particular values at which they settled determine everything. The masses of particles, the strengths of forces, the rules of chemistry, the structure of atoms, the possibility of life. Everything we know about the universe is a consequence of the specific vacuum state the fields currently occupy. But here is the question that physicists have been asking with increasing urgency since the discovery of the Higgs boson. In 2012, at the Large Hadron Collider at CERN, what if our vacuum is not the true ground state? What if the ball has not rolled to the bottom of the hill? What if it is sitting in a dip, a local minimum, a shallow depression partway down the slope? From inside the dip, everything looks stable. The ball is not moving. The walls of the dip are high enough to contain it. You could wait for billions of years and the ball would appear to be perfectly at rest. But just over the ridge, hidden from view, there is a deeper valley. A lower energy state. A truer vacuum. This scenario is called a false vacuum, and our universe may be living in one. The concept comes directly from the physics of the Higgs field. The Higgs field is not like other quantum fields. It has a non-zero value even in its ground state. While most fields settle to zero when there are no particles around, the Higgs field settles to a specific non-zero value, approximately 246 billion electron volts. This non-zero value is what gives particles their mass. The electron, the W and Z bosons, the quarks, they all acquire mass by interacting with this background Higgs field. Without it, they would be massless, and the universe would be unrecognizable. There would be no atoms, no chemistry, no structure, no life. The shape of the energy landscape of the Higgs field, what physicists call the Higgs potential, determines whether our vacuum is truly stable. If the Higgs potential has a single minimum, a single lowest point, then we are safe. The field has settled into the only valley there is. There is nowhere else to go. But if the Higgs potential has a second minimum, a deeper valley at some very different field value, then our vacuum is metastable. It is a false vacuum. The field is sitting in the wrong valley, and quantum mechanics provides a mechanism for it to escape. Here is what the data says. The stability of the Higgs potential depends critically on two measured parameters: the mass of the Higgs boson and the mass of the top quark. The Higgs boson was measured at approximately 125.1 billion electron volts. The top quark mass is approximately 172.7 billion electron volts. When you feed these numbers into the renormalization group equations that describe how the Higgs potential changes at very high energies, something disturbing happens. The potential curves downward. At extremely high field values, far beyond the scales probed by any particle accelerator, the Higgs potential appears to dip below the value of our current vacuum. There appears to be a deeper minimum, a truer ground state. The calculation is delicate. It depends on the precise values of the Higgs and top quark masses, and the current experimental uncertainties leave room for our vacuum to be either metastable or sitting right on the boundary of absolute stability. But the central estimate, using the best measured values we currently have, places our universe in the metastable region, not deep in the danger zone, not obviously doomed, but not safely on the stable side either. We are balanced on a knife edge. The universe appears to be living in a false vacuum that has persisted for 13.8 billion years. Not because it is permanent, but because the barrier between our vacuum and the deeper one is high enough to make the transition extraordinarily unlikely on human timescales. But unlikely is not impossible. And in quantum mechanics, unlikely events happen given enough time and enough space. The mechanism by which the transition could occur is quantum tunneling. This is the same phenomenon that allows particles to pass through energy barriers they classically could not surmount. It is the mechanism behind radioactive decay, where a nucleus trapped behind a potential barrier spontaneously emits an alpha particle by tunneling through the wall. It is the mechanism behind the nuclear fusion in the core of the Sun, where protons tunnel through their mutual electromagnetic repulsion to fuse into helium. In the case of vacuum decay, the tunneling is not performed by a single particle. It is performed by the Higgs field itself. At some random point in space, through a quantum fluctuation, a microscopic region of the Higgs field could tunnel through the energy barrier separating our false vacuum from the true vacuum. It does not need an external trigger. It does not need a cosmic collision or a laboratory accident. It just needs the random, statistical inevitability of quantum mechanics operating over vast stretches of space and time. Given a large enough universe and enough time, the fluctuation will happen somewhere. When it does, a tiny bubble of true vacuum nucleates. Inside that bubble, the Higgs field has a different value. The constants of nature are different. The masses of particles are different. The forces are different. The rules that allow atoms and molecules and chemistry to function no longer apply. Inside that bubble, our physics is dead. And the bubble grows. Because the true vacuum has lower energy than the false vacuum, the bubble wall accelerates outward. The energy difference between the two vacuum states drives the expansion. The wall of the bubble is a phase boundary, a frontier between two incompatible versions of physics, and it moves outward at a speed that rapidly approaches the speed of light. In many models, the wall reaches the speed of light almost immediately after nucleation. Once it does, nothing can outrun it. No signal, no warning, no information of any kind can travel ahead of the expanding bubble. The speed of light is the cosmic speed limit, and the bubble wall rides it like a surfer on a wavefront. This is the nightmare scenario, because light is also the carrier of information. If the bubble wall moves at the speed of light, then the light from the approaching wall reaches you at the exact same instant as the wall itself. You cannot see it coming. You cannot detect its approach. There is no astronomical early warning system. No observatory will spot the incoming front and issue an evacuation order. There is no evacuation. There is no response. The bubble wall arrives with zero advance notice. What happens at the wall is not an explosion. An explosion is a rearrangement of matter within the existing laws of physics. The wall of a true vacuum bubble does not rearrange matter. It rewrites the laws. As the wall passes through a region of space, the Higgs field in that region transitions to its new value. The masses of all particles in that region change instantaneously. Electrons may become heavier or lighter or massless. Quarks may gain or lose mass. The W and Z bosons may shift to entirely new values. The delicate balance of forces that holds atoms together. The electromagnetic force binding electrons to nuclei. The strong force binding quarks inside protons. The weak force governing radioactive decay. All of these are recalibrated in an instant to values dictated by the new vacuum. The result is not destruction in any conventional sense. It is dissolution. The atoms in your body do not explode. They simply cease to be valid configurations of matter. The electron orbitals that define chemical bonds are determined by the mass of the electron and the strength of the electromagnetic force. Change those parameters and the orbitals vanish. The bonds break, not violently, silently. The protons inside your nuclei are held together by a balance between the strong force and the electromagnetic repulsion of their positive charges. Shift that balance, and the nuclei fall apart. Or they collapse into something denser. Or they transmute into configurations that have no analog in our current physics. The molecules that encode your DNA, that store your memories, that maintain the electrical patterns of your thoughts, they unravel. Not because they were hit by something, but because the rules that allowed them to exist have been replaced by rules that do not allow them. It is not death in the biological sense. It is ontological erasure. You do not die because your heart stops. You cease to exist because the concept of a heart becomes physically impossible. And the bubble does not stop. It keeps expanding. It crosses the solar system in hours. It crosses the galaxy in 100,000 years. It crosses the observable universe in tens of billions of years. Everything it touches is rewritten. Stars, planets, black holes, the cosmic web of dark matter and galaxy clusters. All of it is converted into the new vacuum state. The universe behind the wall is not empty in the way we understand emptiness. It is filled with a new physics. A physics we cannot predict in detail because we do not know the properties of the true vacuum. It might support its own forms of structure. It might not. It might be a featureless, homogeneous sea of energy with no stars, no atoms, no complexity. It might be something stranger. We simply do not know. What we do know is that nothing from our universe, no pattern, no structure, no information, survives the transition. Now we can see what every instability was pointing toward. Each mechanism we explored was a symptom of this final vulnerability. The vacuum can be forced to create matter because it is a dynamic system with energy stored in its fields. The constants of nature are not fixed because they are properties of the vacuum state, and the vacuum state is contingent. The very definition of what exists depends on the observer, because particles are excitations above a vacuum state that is itself not absolute. Every crack, every bend, every shimmer was a warning that the foundation is not bedrock. And false vacuum instability is what happens when the foundation gives way. The vacuum state that sets the constants, defines the particles, establishes the forces, and permits the existence of atoms, chemistry, and life may not be permanent. It may be a metastable arrangement that has persisted for 13.8 billion years only because the quantum tunneling probability is extraordinarily small per unit volume per unit time. But that probability is not zero. It is never zero. And the universe is very large and potentially eternal. This is not a collection of separate curiosities. It is a single escalating argument. The vacuum is not empty. The vacuum is not passive. The vacuum is not objective. And the vacuum is not permanent. Each statement follows from the last. Each mechanism deepens the same instability. And the final statement is the one that contains the existential threat. If the vacuum is not permanent, then nothing is permanent. Not the laws of physics, not the structure of matter, not the possibility of life, not the existence of the universe as we know it. The question that remains is not whether this can happen. The mathematics is clear. Quantum tunneling of the Higgs field through a potential barrier is a well-defined, calculable process. Sidney Coleman and Frank DeLucia worked out the detailed dynamics of vacuum bubble nucleation in 1980. The instanton solutions describing the tunneling process have been studied extensively. The decay rate per unit volume per unit time has been estimated. For the current best fit values of the Higgs and top quark masses, the lifetime of our false vacuum is estimated to be extraordinarily long, vastly exceeding the current age of the universe. We are not in immediate danger. The probability that a lethal bubble nucleates within our observable universe in the next billion years is vanishingly small. But vanishingly small is the same language we used for the Schwinger Effect. It is the same language we use for all quantum tunneling processes. Uranium decays because the probability of alpha particle tunneling is small, but non-zero. Given enough nuclei and enough time, it happens with statistical certainty. The universe contains roughly 4 times 10 to the 80th atoms in the observable volume alone. It may be spatially infinite, and it may last forever, or at least for timescales that dwarf the current age by factors so large they become meaningless to the human mind. On those scales, vanishingly small becomes inevitable. There is also the possibility that the transition could be triggered rather than spontaneous. High-energy collisions, the kind that occur in particle accelerators or in extreme astrophysical environments, could, in principle, provide the seed. If a collision concentrated enough energy in a small enough volume, it could push the Higgs field over the barrier locally, nucleating a bubble. This was a genuine concern when the Large Hadron Collider was being commissioned. Physicists calculated the probability and concluded it was negligible, partly because cosmic ray collisions at far higher energies have been bombarding planets and stars for billions of years without triggering vacuum decay. If it could happen easily, it would have happened already. But again, negligible is not zero. And the difference between negligible and zero is the difference between safety and faith. Perhaps the most unsettling aspect of false vacuum decay is not the destruction itself. It is the silence. The Schwinger Effect is violent but local. Vacuum polarization is subtle but measurable. Hawking radiation is faint but detectable in principle. The Unruh Effect is real but too weak to notice. Each mechanism gave us at least the theoretical possibility of seeing it, measuring it, responding to it. But vacuum decay offers nothing. No signal precedes the wall. No tremor in the fields warns of the approaching front. The transition could have already begun a billion light years away. A bubble of true vacuum could be racing toward us right now, consuming galaxies, rewriting space-time, annihilating the possibility of chemistry and thought. And we would have no way of knowing until the instant it arrived, which is the same instant we would cease to exist. We began this journey with a simple observation. You trust empty space. You trust that the void between atoms is harmless, that the vacuum is passive, that nothingness is the safest thing in the universe. We have now shown that every part of that trust is misplaced. The vacuum is not empty. It seethes with virtual particles that can be promoted to real particles under sufficient stress. The vacuum is not passive. It actively screens charges, modifies constants, and generates the mass in your body. The vacuum is not objective. Its particle content depends on who is looking and how they are moving. And the vacuum is not permanent. It may be a temporary phase, a false ground state perched above a deeper minimum that would erase the laws of physics if the transition ever occurred. The 5 mechanisms we have explored are not 5 separate warnings. They are 5 chapters of the same warning. The vacuum is the most important substance in the universe. It defines what exists, how it behaves, and whether it can persist. And every tool we have built to study it, every equation we have solved, every experiment we have run, tells us the same thing. The vacuum is unstable. Not violently unstable, not obviously unstable, but conditionally unstable, metastable, balanced, held in place by the height of an energy barrier and the smallness of a tunneling probability. It has held for 13.8 billion years. It may hold for trillions more, but the mathematics does not promise forever. The mathematics promises only that the probability is small. And in a universe that may be infinite in space and eternal in time, small probabilities are not reassurances. They are countdowns. The void beneath your feet, between your atoms, inside your skull, it is not the absence of danger. It is the most elaborate and precarious balancing act in the history of existence. Every force, every constant, every particle mass, every chemical bond in your body is a consequence of the vacuum being in this particular state. If the state changes, you do not adapt. You do not evolve. You do not survive. You dissolve into a reality you cannot comprehend, governed by laws you have never encountered, in a universe that has no memory of you. The vacuum is not the floor beneath reality. It is a trapdoor held shut by probability, and you are standing on it right now.